For Chapter 19 reassessment, I used 4 homework problems to explain aspects of 4 different circuits. In this first situation, the circuit consists of 1 battery and 3 wires of the same material with different areas. The wire from A to C and E to G are identical but differ from wire D. Because the right and left wires are identical, I know the magnitude of the electric field on the right wire equals the magnitude of the electric field on the left, and ultimately allows me to refer to both of these wires as wire F. Although the magnitude of the electric field at location D does not equal the magnitude of the electric field at any other location, the electron current at D does equal the electron current at other locations of F. Using the current conservation rule, I was able to set up an equation to relate the currents of D and F to the magnitude of the electric field. I found a value to relate these quantities, and by using the value in the loop rule, I found the magnitude of the electric field at location D. Finally, I plugged the values into the electron current equation and solved for the current at location D. In situation 2, the current consists of 2 batteries and 2 identical wires. The magnitude of the electric field at a point on wire F equals the magnitude of the electric field at a point on wire C. The electric field points along the wire from the positive end of the battery to the negative. Once again, I used the loop rule to find the magnitude of the electric field at this point. I used the electron current equation to find how many electrons per second entered the positive end of battery 2. Because the wires are identical in this circuit, increasing the cross-sectional area would not affect the magnitude of the electric field. There is, however, a buildup of charge on the surface of each of the 4 corners, and nearly double the buildup of excess on the surface on each side of both batteries. In the third situation, this circuit consists of 2 batteries and 2 nanochrome wires of different areas and lengths. First, I started with the current conservation rule to relate the magnitude of the electric field of the thin wire to the magnitude of the electric field of the thick wire. I used this value in the loop rule to find the single values of both the thick and thin wires. In order to find the time it takes an electron to drift through the 2 wires from location B to location A, I used the magnitude of the electric field and the electron mobility to find the velocity for each wire. I divided the length of each wire by its corresponding velocity to find the time in seconds. I added the 2 components together, and for this problem converted the time into minutes. I know it had to take at least 1 nanosecond before this circuit reached steady state after being assembled, because the information could not be received throughout the wire faster than the speed of light. By plugging in the values of the electron density, the electron mobility, the magnitude of the electric field, and the cross-sectional area into the electron current equation, I would once again be able to find how many electrons cross the junction between the 2 wires every second. The final situation is very similar to the in-class standard. The circuit consists of 2 batteries and 3 identical light bulbs. There are 3 equations which can be formed using the energy conservation rule. The first loop would be the outer loop, which is the 2 batteries, bulb 1, bulb 2, and returning back to the 2 batteries. The second would be the inner loop, which is the batteries, bulb 1, bulb 3, back to the batteries, and the third loop would be bulb 2 and bulb 3. The current conservation rule forms yet another equation, which is the electron current at location at bulb 1 equals the sum of the electron current at bulb 2 and bulb 3. The EMF value of each battery is 1.3 volts. The length of the filament in each bulb is 9 millimeters, and the radius is 5 times 10 to the negative 6 meters. Given the electron mobility and density, I then chose 2 of the energy conservation equations and 1 charge conservation equation to solve for the magnitude of all 3 electric fields. Then I used the electron current equation to find the current in each bulb. I could have also solved only for the magnitude of electric field and electron current at bulb 1, and then divided by 2 to find the magnitude electric field and electron current values for both 2 and 3 because of the symmetry in this circuit.